Hello everyone. We are Communication and Electronics Engineering students at Beirut Arab University, Tripoli.
My name is Yasmin Izzuddin. I will present for you with my colleague Wissam Abed, Isam Sanjadar and Ibrahim Mir'i the source coding including the entropy, the classification of codes, the Huffman coding and the Lempel-ziv coding.
I will start now by defining the information theory, how to do it, and how to measure the information content. The information theory, the major goal is for one person, a transmitter, to convey some message over a channel to another person, the receiver. To do so, the transmitter sends a series partial message to give clues towards the original message. The information content is for one of these partial message is a measure of how much uncertainty this resource for the receiver. And now we are giving a discrete random variable x and possible x1, x2, xn and an associated probability p1, p2 to pn. The probability that x will take on the value x1 is given by the probability p1, the value x2 by probability p2, and so on. The smaller the probability, the more uncertain it's that x will take on that particular value. Claude Shannon, in his seminal work on the theory of information, defined the information received when learning that x had taken on the value xi as ixi equal log base 2 for 1 over pi and the unit is byte. I will talk now about the entropy. The entropy formula is as shown: hx equal minus summation px log base 2 of px. What is the entropy? The entropy is a minimum number of bits used to represent a symbol at the transmitter in order to receive it with no error. The unit of entropy is bit, and on what entropy depends, it depends on the probability of x. We have now this illustration that represents the average number of bits used to transmit choice a function of bits. What will happen if we use less than hx? If we use less than hx, we will have an error at the receiver. And if we send on the average but more than hx, we will not use our resource properly. And if we send on the average exactly hx, it's perfect for log. And now we have the binary entropy function in function of probability. And when h equal 0, there are no uncertainty. When h equal 1, there are the most uncertainty, 1 bit for binary information.
I will present for you the classification of codes. Codes can be classified into 7 types. Classification of codes is best illustrated by an example. So we will take a source with size 4 encoded in binary symbols with 0 and 1. We will have here 6 codes: code 1, code 2, code 3, code 4, code 5, and code 6, with code words x1, x2, x3, and x4. Between parentheses, this example illustrates all the 7 types, so we will try to find them for a better memorization. The first thing that can come into your mind while looking at this table for the first time is that there are codes with same length and code with different lengths. So the first 2 classifications found till now are fixed length code, just like code 1 and code 2 with length equal to 2, and variable length codes just like code 3, code 4, code 5, and code 6. Note that a code can only be a fixed length code or a variable length code, but not both. The third classification we can make is that in the same code, there are code words that are repeated several times. Look, for example, at code 1. We have x1 equal to 0, 0, and x3 is also equal to 0, 0. So here we have found our third classification, distant codes. A code is distant if each code word is distinguishable from other code words. All codes here are distinguishable except for code 1. The fourth classification we can make looking at the table is that there are code words that can be formed using other code words. Look for example at code 3. We have x3 which is formed by using two x1s, and we have x4 which is formed using two x2. So here we have our fourth classification, the prefix-free code. A code in which no code word can be formed by adding code symbols to another code word is called a prefix-free code. Thus, in a prefix-free code, no code word is a prefix of another. Here we have code 2, code 4 and code 6 that are a prefix-free codes. The fifth classification we can make now is that in the same code there are binary sequences that can be decoded using different code words. Look for example at code 3. Look for example at code 3. If you have the binary sequence 1, 0, 0, 1, one can decode this binary sequence using 1 corresponding to x2, 0 corresponding to x1, 0 to x1 and 1 to x2, while another source can decode the same code using 1 to x2, 0, 0 to x3 and 1 to x2. So here we have our fifth classification, the uniquely decodable code. A sufficient condition to ensure that a code is uniquely decodable is that no code word is a prefix of another. Note that the prefix-free condition is not a necessary condition for unique decodability. Thus, code 2, code 4 and code 6 are uniquely decodable. Code 3, as mentioned before, isn't a uniquely decodable code. Code 5 doesn't satisfy the condition of prefix-free code, and yet it is uniquely decodable since the bit 0 indicates always the beginning of the code word. Till now, we have found the first 5 classifications. The remaining 2 are somehow difficult to detect from the table, so we will illustrate them directly. We still have instantaneous codes. A code is called instantaneous if the end of any code word is recognizable without examining subsequent code symbols. Prefix-free codes are sometimes called instantaneous codes, and our seventh classification will be optimal codes. A code is said to be optimal if it's instantaneous and has minimum average length L for a given source with a given probability assignment for the source symbols.
I will present for you Huffman coding. First, what is Huffman coding? Huffman coding is a simple and systematic way to design a good variable length code given the probability of the symbols. Where is used the Huffman coding? We can use Huffman coding and compression of image like JPEG or video compression like MPEG. So, how can we design a system using Huffman coding? We will explain this point through an example. And now we will solve this example. First, we have 4 symbols: S1, S2, S3, and S4. And with their probability, and we will sort them by descending order. We will start by the 2 last probability and we add them, and the result we will compare with the 2 other probability, and in this case we have the same number, 0.25 and 0.25, so we will put the new one first. And the second one, and we put 0, 1. And we will do the same process for the last number, we put here 0, 1, and we get here 0, 1. And now we will compute the code word. First, S1, we will see the path of S1. Here there is 1 only. So the code word is 1. For S2, we'll start from here. We found 1. And we found 0. So we will write the code 0, 1 from the right to left, and so on for S3 and S4. To calculate the length, the average length, we write the formula or the equation Lx equal sigma Pix times Nx. Pix is the probability, and Nx number of bits. So we will start by the first probability 0.5, and we will multiply it by the number of bits, and it's 1. So 0.5 times 1 plus the second one is 0.25, and we will multiply it by number of bits is 2 times 2, and so on, and we get L equal 1.75. And now we will calculate the entropy. The entropy equation is minus sigma Pi times log Pi. The Pi is the probability. So h of x equal minus 0.5 times log of 0.5, it's log base 2, plus 0.25 log base 2, 0.25, and so on. And the final answer is 1.75. So to calculate the efficiency equal h of x over Lx. So 1.75 over 1.75 equal 1. So we can conclude that Huffman coding is efficient for this case.
Why should we use the Lempel-ziv algorithm instead of the Huffman coding? The Huffman coding requires 2 passes through the data to encode it. The first pass is to compute the frequencies of all the letters, and the second pass is for actually encode the data. While the Lempel-ziv algorithm constructs its dictionary on the fly, so it's enough to pass through the data once to encode it. I will present for you now the Lempel-ziv 78 algorithm. The idea behind all the Lempel-ziv algorithm is that if some text is not uniformly random, that means if all the letters of the alphabet are not equally likely to appear, then a substring that has already been seen is more likely to appear than a substring that hasn't been seen before. The Lempel-ziv 78 algorithm works by constructing a dictionary of substrings, which we will call phrases, that have appeared in the text. Here we can see a set of data that we would like to encode using the Lempel-ziv algorithm. So we will start by AB. AB has been seen before, so we take ABB, then B, then ABA, then AB, then BB, and then ABB, we have seen it before, so ABBA, and finally BB. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 positions. 1, 2, 3, 4, 5, 6, 7, 8, and 9. We write here the sequence A, AB, A, BB, then B, A, B, A, A, B, A, B, 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 A, B, B, A, and finally B. Numerical representation. We first start with putting phi A, as A is a reference to compute the Lempel-ziv algorithm and B is the second reference. AB, it's 1B. ABB is 2B. B is phi B. ABA is 2A. Then ABAB, it's 5B. Then BB is 4B. ABBA is 3A. And finally, BB is 7. And here we write the binary code used in Lempel-ziv algorithm. I have written before that A equals 0 and B equal 1. So we use here 0, then 0, 1, 1, 2 is 1, 0, and B is 1. Phi is usually 0, 0, and B is 1. 2 is 1, 0, and A is 0. 5B is 1, 0, 1, and B is 1. 4B is 1, 0, 0, and B is 1. 3A is 1, 1, 0, and finally 7 is 0, 1, 1, 1. Thank you for your attention.